Hi, I just want to steal the attention from the two of you for 1 second. I'm Karsten, hello, I'm one of the two rump session chairs. I am here to remind you that you should all submit a rump session talk until tomorrow at noon. The more entertaining the better. If you want to sing, if you want to dance, if you want to read a poem, if you want to, I don't know, break anything on stage, if you want to just demonstrate your most recent results and show them to everybody, that's also fine. The more fun, the better. Please submit, and then we can have the best rump session that we ever had at Eurocrypt here in Madrid. So, thank you, see you tomorrow.
Thank you, Karsten. So my name is Lejla Batina. I'm chairing this session on masking. So welcome to this session. We will have 4 talks, and the first one is on new techniques for random probing security with application to Raccoon, which is one of post-quantum schemes. And we have 2 presenters, Sonia Belaid and Melissa Rossi. The floor is yours.
Thank you. So yes, Melissa and I will present this work that we wrote with Mathieu Ridin. So the presentation will be organized into 3 steps. First, I will discuss masking countermeasure and the random probing model to reason on the security of masking schemes. Then I will talk about the composition in this model for mask schemes. And then Melissa will show you how we can build a random probing secure implementation of Raccoon. So first, masking. So masking is one of the most deployed countermeasure to thwart side channel attacks, which exploit the physical leakage of a device to recover secret data. So for any sensitive variable X, we split it into n shares, like this, such that the sum, for instance, gives the sensitive value. Masking makes it exponentially hard for an attacker to recover the sensitive data from individual leakage. And to sample encodings like this, we just need to sample uniformly at random n-1 shares and compute the last one to preserve correctness. For linear operations, it's very simple because we just have to apply the linear operation on each share individually. And for nonlinear operations, it's trickier, like the multiplication gadget represented on the right here. It's trickier because we have to get complex operations involving additional randomness, like this R here, to maximize the security of such schemes. And once we have a masking scheme, we have 2 options to assess the security. Either we go for physical measurements and concrete attacks on actual devices, or we try to model the attacker view to build a theoretical security proof. And in this talk, we'll focus on this second option. So now my objective is to show you how to model this attacker view. So I still rely on this example of a multiplication gadget here between 2 data, X and K, that are each split into 2 shares. And I will show you 2 views. So on the left, we have the attacker view. The attacker is represented here by Melissa, and she has access to nothing at first, no intermediate value. And my view here, the reality, so I have access to all the secret value of the circuits that is representing the gadgets in the middle. And so, as I said, Melissa has only the circuit at first, but with side channel attacks, we'll give her some leakage. And the goal to prove the security of a masking scheme is to show that Melissa cannot recover information about the secret data X and K. So for that, we have to specify how is the leakage that Melissa receives. So we have many leakage models in the literature, but here I give you the 3 most common ones, let's say. I will discuss briefly the noisy leakage model, which is pretty close to the reality of embedded devices. Specifically, we assume that Melissa here is given the noisy functions of all the manipulated data in the circuits. So how does it look like? It's close to a consumption trace where we have approximate value for all the wires in the circuit here. This model is very realistic, but it's very hard to make security proofs within it without making strong assumptions. That's why, in practice, we rely on an easier model, simplest model, that is called the probing model, introduced by Ishaisen and Wagner at Crypto 2003. And in this model, Melissa is only given t variables with their exact value. So for instance, here, since we have two shares, we can assume that t equals 1, and I can ask Melissa to choose the wire that she wants to get. And so if she chooses this one, I just have to give her the correct value, which is x2 times k1, which gives no information on the secret. So most of masking schemes are proven to be secure in this model. The point is, even if it captures the fact that it's difficult to combine individual leakage, it does not capture some attacks, like horizontal attacks, which exploit several values in the same circuit, several same values in the circuit. So in the middle, we have the random probing model, where Melissa is given all the variables of the circuit, but with probability p. And the nice feature of this model is that we have a reduction with the probing model and the noise leakage model. Namely, if a circuit is secure in the probing model, it's also secure in the random probing model for some probability, and in the noise leakage model for some noise. And the point is that the reduction here is not super tight because it depends on the size of the circuit, but this one is better. And so while most of masking schemes are today proven secure in this model, we now try to make them secure in the random probing model to get closer to the reality. So this is the objective of this talk. So now I focus only on the random probing model. So a reminder, Melissa is given now each wire with probability p. And the idea is to show that with this leakage that she has, plus the circuit, she cannot recover the values of x and k. How can I build a security proof in this model? Well, the idea here is for me to simulate the leakage that Melissa has without the knowledge of the secrets. If I manage to do that, it will show that the leakage of Melissa won't bring information about the secret values. So let's take a few examples.
So yes, let's see examples. So on my side, I see that there are 19 wires, and so it's almost around 2 to the 19 possibility, depending if one wire is taken or not. So for example, a case could be that I get nothing, so empty space, empty set.
And this case, of course, is easy to simulate for me.
Yeah, bad luck for me. The second example here, yeah, I have more hope because there are 3 probes and they depend on a lot of shares that are input, and 3 is more wire than I can get with T probing model where T is reduced to 1.
But I can show I can still simulate this case, because if I assume that the sharings are generated randomly, as I explained before, I can just have a uniformly random value for K1, another for X2 without the knowledge of the secrets. I can simulate this probe plus this one from these 2 values. And I can simulate this one because the addition is modulo Q, for instance, here, which is prime, so it's bijective with the random value here. And then I did all the simulation here without the knowledge of the secret at all.
Done. So let's see another example. Here I'm pretty sure I can get the secret because I get K1 and K2, and so if I sum them together, then I know the secret key K.
And exactly, Melissa wins in this case. But the point for me is that Melissa wins, but only with probability epsilon. So the only cases where I cannot simulate the leakage without the knowledge of the secret must be very low, with very low probability. And so I must ensure that this happens very rarely. And in practice, we can choose to prove the scheme with a very low epsilon, just like for the black box security proofs. So now we showed how to build a security proof for a small circuit. I would like to talk to you about the composability. So if we have bigger circuits, like bigger schemes, AES, Raccoon, we need to assemble a small gadget like this one. And for that, we need a stronger property on each individual gadget to ensure the composability. So this stronger probability will exploit the simulation from the input shares. So basically, instead of saying I can simulate the leakage of Melissa without the knowledge of the secrets, I will say I can simulate Melissa's leakage and some outputs from a certain number of input shares, except with probability epsilon. So here, we can take the same examples of these 3 probes. And if I don't assume anymore that the shares are generated randomly, I can show that I can simulate these three probes from K1, the first share of K, X2, the second share of X, and this one randomly. So I used only one share for each input, which is OK. Of course, with the last examples that we have had before, for this one, I cannot simulate them without the knowledge of only one share of K. So for this simulation, I fail. So I need to count this case into the epsilon that we have for the security. So to show you how it goes for a big circuit, so imagine here you have a big circuit G with a lot of gadgets, just like the multiplication before. All these gadgets fulfill the composition property that I showed you, which is called threshold RPC. And the point is that with this property, we can propagate the leakage in the outputs of each gadget. So for instance, here for G8, and we can continue. And this makes it possible to show that all the leakage of the individual gadgets can be fully simulated with at most T shares of each input. Of course, except with probability epsilon. The point with this property is that it scales with the number of gadgets, because as soon as we fail the simulation for one gadget in the global circuit, we completely fail. So we have to consider this number. So this is a first composition that I told you about, which considers the threshold, but we had another composition tighter in the literature. The principle is always the same, meaning that we have internal leakage, we have some outputs that I give to Melissa, and we need to evaluate how it goes for the input, what input I need to simulate the leakage and the outputs the attacker has. And for that, the property that I told you before is based on a threshold T. So we have, Melissa has T outputs, she has some leakage which depends on the probability P, and I want to evaluate how many input shares I need to compute to simulate this leakage. The second property that we had in the literature is general RPC. It's much tighter because instead of considering a threshold on the output shares and the required input shares, it considers all the possible sets. So we list all the possible sets of output shares, all the possible set of input share, and we have a matrix with the probabilities of each scenario, the input set that we need to generate the leakage plus output shares. This is very nice because it's tighter in terms of security, but unfortunately it doesn't scale when the number of shares increase or when the composition is complex. So in our paper, we introduced an intermediate property that we call cardinal RPC. Instead of considering all the possible sets of output shares or input shares, we consider the cardinalities. And while it's obvious that it's an intermediate step, it has a nice trick making the simulation very efficient to make. So considering the cardinalities instead of the sets make it possible to compose in complex circuits. So we will rely on this property to build Raccoon secure, random probing secure implementation.
Yes, so now I will talk about how to apply this framework to Raccoon. So actually, we wanted to apply it to a post-quantum scheme, and Raccoon was a good starting point because it has been introduced to be side-channel friendly, to be masking friendly. It has been introduced a few years ago. And it is quasi-linear in the masking order. So as you can see in this graph, when the number of share increases, the red curve is nice and flat compared to the blue curve that is the lithium that rapidly explodes with the number of shares. So Raccoon can be seen as a masking-friendly alternative to dilithium. It has been proved in the D-1 probing model, so the model that was introduced before by Sonia. It has been published in Crypto last year. And it has the same assumption of, as dilithium, now called MLDSA. This has a price, of course, and you can see the price is pretty obvious. It's on the modulus Q here. That is very large. And the signatures are also 4 times larger. It was not selected, it was submitted to the NIST additional post-quantum signatures, but it was not selected. It's because if we take all side channel consideration apart, it's slower than dilithium. So that's logical. and how Raccoon works. You take dilithium and you simplify it until it's masking friendly. So let's look at the key generation, for example. You simply generate a large matrix A, and then you take S, a secret that is 0, and you add noise to it, and then you multiply the matrix A with the secret S, and you add noise again. And that's all. You have the public key here. Public key is T. When I say add noise to a vector, is adding some small uniform. So here, 2, it is a simplified version of dilithium. And the more uniform you add, the closer you get to a Gaussian distribution, like you can see in the purple curve here. For the signature, you take the first 5 steps of the key generation and you apply them to the first 5 steps of the signature. It's exactly the same. And after there is unmask computation and then a linear combination of masked values. And then you have the signature. The good thing is that there is no rejection sampling here. So it was a good target for our framework that was pretty theoretical. So we looked at Raccoon from a functional point of view. Here we didn't care about the T-probing security. So from a functional point of view, we can remove the refresh because it's an identity function. And we looked at all the operations. And fortunately, we can write Raccoon pretty easily with additions and scalar multiplications. As you can see, it's almost adding noise is addition, and multiplication with matrix is a lot of scalar multiplications. There is one copy gate here because we reuse a variable at some point, but that's pretty simple. So, and we also had to introduce a new notion for capturing some extra information that was not captured in the previous model that Sonia presented. The attacker, myself, also has extra information, like public outputs. For example, I get the public key, I get the signature, and I even can get internal values. So this notion was previously introduced in the context of T-probing model, and here we had to apply it to the random probing model. We also had to include auxiliary inputs because the noise that we have doesn't have a uniform distribution over the whole field, so we had to consider it apart. So once we have this new notion, we could build the gadgets. So it's only 3 gadgets, addition, multiplication, and copy. And you see we could make them pretty easily with elementary gates. The only problem is the refresh. Here you see that I removed the refresh earlier, but it comes back here. And it's non-optional to get composability. So we were looking for a random probing efficient refresh, but we had to introduce a new one. To that for this purpose. So let's see it on an example. We take a Z, which is 8 shares. We start with 0. And then we draw 2 indexes, for example, 3 and 7, and a random R1. And so we add it to the 3rd index and remove it to the 7th. And then we do it again, and so on. So you can see that at some point, we stop at a certain iteration. At some point, some indexes will be touched several times, and some indexes will never be touched. So this is not good if you're familiar with the T-probing model, because then if there is a share that is always 0, then it's a problem. But in the random probing model, everything is probabilistic. So this was okay for our purpose. And we could compute the composability advantage. This epsilon that we talked earlier, the epsilon of the failure simulation. And we saw that the probability of simulation decreases when we increase the number of iterations up to a certain threshold. And then we could apply it to a Raccoon signature scheme. We could estimate the number of randomness, the number of additions, in order to get 128 bits of security. So getting is this epsilon as low as 2 to the minus 128. But the cost is pretty high. We saw that the number of randomness is times 2,000, so it's high. But it's a good threshold compared to existing generic techniques. And yeah, it's going towards implementations of random probing secure implementations. Oh, and the probability is 2 to the minus 24. It's important to note it. It's very low, and it's, for now, not really realistic for concrete devices. So to conclude, what is the state of the art today for random probing? We have elementary gates, addition, multiplication, copy, and refresh. It's possible to combine them by combining the probability that we called this epsilon. We computed the complexity and penalty factor for Raccoon, but there is much to do ahead. Taking a step back and looking at more advanced gadgets to get more efficient versions. Look at composition. There are many other composition papers that have been published, and it would be interesting to compare these techniques to see if there is one that is better for our purposes. Formal verification remains, and I cannot say that we ticked the efficient implementation box, so that still remains to be done. Thank you.
Is there a super short question for Melissa? No? Then we just continue and maybe take your question.
Thank you.
You have a question? Yes. Okay, just a quick one. Yeah.
I'm wondering how does can your technique be applied to pullover hash and assign masking friendly signature?
To other masking friendly signatures?
Yes. Yeah, pullover.
You want to? Okay.
Yeah, that's a good question, and I think it could be applied similarly. We would have to look at it, but I think that the building blocks are similar with the add-rep noise and all these blocks, so it could be applied.
The only point is that here with Raccoon, we don't consider nonlinear operations. So if we have schemes that have nonlinear operation, we will have to design a specific gadget for it that we don't have right now. We only have addition, copy, and refresh it. And scalar multiplication, but not nonlinear ones.
Let's thank the speakers again.
Thank you.
Our second talk today is Julius Kam, yes, is on generic framework for side channel attacks against LWE-based crypto systems. And speaker is Julius Hermeling. I'm waiting. Yeah, he's gonna get his mic in a sec. But yeah, you can see the title slide is already there. So we'll hear all about it in a minute.
Thank you for the introduction. This is joint work with Silvan Streit, Erik Mortensen, and Richard Petri. Our work concerns the question on how to deal with side information in lattice-based schemes, so side channel information that we get from a side channel attack. And several previous frameworks have actually already, presented generic frameworks for this, and many of them have essentially been based on the primal attack. So they define hints, and these hints can be integrated into the lattice instance, and then we get an easier to solve lattice problem. But unfortunately, sometimes in such an attack, or rather often, we get information on Hamming weights that is noisy. And in these cases, these frameworks sometimes are not optimal. So these do explain on how to deal with noisy information, of course, but if this is on the Hamming weights, then we get a very strange looking distribution on values, then these frameworks are not necessarily optimal. Another technique that has been often used in side channel attacks on LWE-based schemes are soft analytic side channel attacks. And these attacks essentially, they use belief propagation to essentially combine the leakage from several intermediates or also over several traces. And in this work, we'll show that we can define hints, as in the lattice-based case, that generalize almost all of these hints that we had in the lattice setting and in the primal attack-based setting. And we can use one belief propagation instantiation to solve them rather generically in most cases. And then we also explain how to use a greedy solver to solve them in other cases. And further, we explain how a recent greedy solver and belief propagation are related. This is especially important if we talk about masked implementations, because here we are even less likely to actually get values or value leakage or noisy value leakage. To give you some context on belief propagation versus greedy solvers, in MLChem we have a noise term. This essentially comes from that we have to recover the message from noisy polynomial coefficients, and this noise term holds information about the secret key. And many attacks that target these noise term, they obtain inequalities in the secret key. So we have a vector v and the secret key x, and the inner product of this v of v and x is smaller or equal than some value b. And previously, this has often been solved for the secret key using belief propagation. This is somewhat similar to how LDPC codes work, just that we don't have low density, in fact, the opposite. And how belief propagation works in this context, so belief propagation updates beliefs and variables, probability distributions based on the information and based on the current beliefs in all other variables. So in this case, if we have an inequality, in belief propagation, we update a value, the belief in a value, using the partial sum of all other values of this inequality and the inequality itself. Now, recent work introduced the greedy solver. And instead of working on beliefs and probability distributions, this works on a guess. On the current on the secret key, and changes to the guess that are ranked by guess scores, and then they apply the best scores, and hopefully this then leads to recovery of the secret key. But in this attack from chess24, actually what the adversary learns is much more. They learn the Hamming weight of the noise term and not just an inequality. They show that you can derive an inequality, but this is not necessarily optimal. In fact, this loses information. So this led to several questions for us. What is the relation between the solvers that do solve the same problem, essentially? Does greedy actually require less information than using belief propagation, as claimed by this paper? And can we somehow do better? Can we use the information that we get on the noise term, the Hamming weight, without deriving an inequality, without losing information here? And what we propose is using distribution hints. So previously we had several hint definitions from these frameworks that essentially use lattice reduction to recover the secret key. And for a known vector x, known vector v and secret key x, what we learn here is either the value of this inner product, the value mod some modulus, the noisy value where n here is a normal distribution, or we learn an inequality, or a short vector hint. And almost all of these hints can actually be written in a different form, in a more general form. What we define are distribution hints. For known vector v, we learn a distribution d. such that the inner product of the vector and the secret key X is distributed according to D. So this is something that could fall out directly out of a side channel attack. For example, we learn the Hamming weight of an intermediate value, or the noisy Hamming weight of an intermediate value. But also all of these hints on the left here, they can be written in this form, except for the short vector hint. We can also directly write the information in this previous attack from chess24 without having to bring this in a form where we lose information. And of course, we can do this for any function f that we have f which gets an input which is linear in the secret key. And whatever information we get, we can write this as distribution hint. Of course, distribution hints are of no use if we cannot solve for the secret key from those distribution hints. And we propose two different solvers here. The first one is a belief propagation instantiation, and the second one is a greedy solver. And the following, I'll always consider one hint that means one vector v and a distribution d, and the inner product of v and x is distributed according to d. And how our belief propagation graphs is, what our belief propagation graph looks is shown on this slide here. We have variable nodes. These variable nodes represent the unknown key coefficients, so the coefficients of x. And for each hint that we obtain, we introduce one check node. This check node represents a hint and will update the probabilities that come from the variable nodes. So these variable nodes are initialized to the distribution that the secret key is sampled from in the scheme that we target. And then they send their beliefs, their probability distributions to the check nodes. The check nodes update each coefficient based on the messages, the beliefs in all the other coefficients, and the distribution hint that they represent. So how this works is to compute the update for xj being xj prime is that we loop over all the values that the inner product can take according to the distribution D. And we sum up the probability of this inner product being A and the probability of the inner product being A according to the other beliefs, the beliefs in the other variables, and the current value that we are computing the update for. So we sum all of these up, and this gives us a new probability for x being xj prime. Each check node does this for all coefficients, and these beliefs are then being sent back to the variable nodes, which combine them and then again send them to the check nodes, and hopefully we converge against the secret key, which should happen if we have sufficient information, sufficiently many distribution hints. Now the greedy solver again works on a guess x prime and changes to this guess. The greedy solver computes change scores for the secret key coefficients of the current guess. And this works actually very similar. To compute the change score for a change c to the coefficient xj, what we do is we again loop over all the possible values of this inner product according to the distribution hint. And then instead of computing the probability of this partial sum, we use the distance that this change would introduce to the value A. We have to do this, but also we have to do this because we don't have probabilities available. But also this has several advantages because we replace the computation of the distribution of this partial sum by a simple distance. And the computation of this distribution is very expensive. So this is computationally very expensive. And actually, if the coefficients of V are too large, we cannot compute this at all. I tried to visualize this here. We can see one distribution hint as a family of hyperplanes through the key space, each of them attached with probability. And now if we want to update value x, the intersection with the plane that comes from x being some value, of course, in the direction of this partial sum can only take one value. So we can write this in or visualize this in a two-dimensional space, where on the x-axis we have the value that we currently want to update, and on the y-axis we now have this partial sum. And the y-axis has probabilities attached to them. They come from the messages, from the beliefs that come from the other variable nodes. And the lines also have probabilities. Those are the hint probabilities. And to update one value, what we do is we add up the intersections with the hints, and we add up the probability of a hint and the corresponding probability for the partial sum for the y-axis here. And this we do for all hints. This is exactly the sum that we had in the previous slide. The greedy may then be solved, seen as a collapsed version of the BP. So in the greedy, to get from the BP algorithm to the greedy algorithm, we replace the probability distributions by the most likely value in this probability distribution. And the updates for the values, for the probabilities for the coefficients are replaced by scores for changes to the guess. And then also we have to replace this sum, which is expensive, which probability distribution is expensive to compute, by a distance. Of course, this loses information, but it gains performance. And actually, we show that in practice, this greedy solver requires more information to solve for the secret key and thereby disprove this previous claim, because our solvers can actually see in special cases of previous attacks. If we instantiate our solvers to decryption failure inequalities, then if we use the belief propagation, we get either this previous belief propagation instantiation that we had for decryption failure inequalities. If we do this for the greedy solver, we get the previous greedy solver from chess24. If we target MLDSA, we actually get another recent chess paper, just that the computation is slightly different here. So the actual computations differ, but the principle is the same. Also for the greedy solver, there's a slight difference, but this is also not very relevant or substantial. So thereby we explain the conceptual relations between these greedy solvers and the belief propagations. And also, of course, our attack can be used to improve this previous attack from chess24, because we don't actually have to derive decryption failure inequalities. We can directly use the distribution hints that we get from the Hamming weight in our solvers. We also cover most hints from the previous paper, and in the cases where we have noisy distributions on Hamming weight, we usually perform better than if we use these lattice reduction-based frameworks. In the non-noisy case, the lattice reduction, unsurprisingly, is usually better. In addition, this applies whenever we have information on a variable that is linear in the secret key. So if we have an intermediate that is linear in the secret key, and we learn f of this intermediate for any function f, then we can express this as a distribution hint and either solve it using the belief propagation if the coefficients of this vector, the coefficients of the linear relations are small, or we can use the greedy solver. We also show how this can be combined with lattice reduction. It has been previously shown that belief propagation and lattice reduction can be combined in lattice-based schemes, and we show how to adapt this for the greedy solver, where it was previously not known how to do this. We have also used this for a second-order attack on a masked MLDSA implementation, and this paper can be found on ePrint. So in conclusion, our framework is, compared to previous frameworks, very generic, and the greedy solver is very efficient. The belief propagation, it depends. We generalize several previous solvers. If we instantiate our solver to previous attacks, we often just get the solver from the previous attack, and thereby we can also explain how the recent greedy solver and the belief propagation are related, and we can disprove this claim from the recent chess paper. In a sense, we also complement lattice-based frameworks because in some cases, these lattice-based frameworks are a bit limited, but in exactly these cases, our framework works better. And I would like to stress that this attack or this framework also works for different types of schemes. So we do not necessarily have to rely, we do not necessarily need lattice-based schemes here. It's just that the subsequent lattice reduction step doesn't work in this case. Also, it's open source, and we provide an easy Python interface. So this should be mostly ready to use. Yeah, thank you for your attention.
Question or a comment? Yes.
Hi, thank you for your talk. I was wondering about the hint of the form V when it's a short vector. Do you use it in your framework?
No, we cannot deal with short vector hints, but as far as I know, those are mostly relevant for n-true.
Okay, thank you.
Let's thank the speaker again. Moving on to the third talk in this session, which is on tighter security notions for a modular approach in private circuits. And it's a collaboration of a number of authors, but Bohan Wang will give the talk and maybe introduce the rest.
Okay, thank you. Hello, everyone. I'm Bohan Wang, and I'm going to introduce our work, tighter security notions for our modular approach to private circuits. This is a joint work with Juelin Zhang, Yu Yu, and Weijia Wang. Let me start with some background about side channel leakage. In real-world scenarios, the adversaries can exploit physical leakage like execution time to gain information about circuit wears. To formally describe this leakage, there are three different models, namely the probing model, the random probing model, and the noisy model. While the noisy model best reflects reality, its security proofs are extremely challenging. The probing model is much easier to analyze. But as shown in the work proposed by Dark, Zambolsky, and Forst and Eurocrypt 2014, there is a significant gap between these two models. That's why in this work, we can focus on the random probing model, where the adversaries samples each wear with probability p. Then let's talk about masking, a powerful countermeasure against side channel attacks. Its core idea is simple. Rather than handling the secret where directly, we split it into multiple randomized shares. Among the masking approaches, the linear masking is the most common one. It splits each secret into n uniform shares and ensures the sum of all shares equals the secret. Notably, masking is not only about data, but also about computation. So every gate in the circuit should be replaced by a corresponding secure gadget that operates on shares. And this replacement operation is called compile. For example, the addition gate with inputs A, B, and output C should be compiled by an addition gadget with input shares A sub 1 to A sub n, B sub 1 to B sub n, and output shares C sub 1 to C sub n, such that the sum of all input shares equals that of the output shares. Finally, let me introduce how the simulation works with the leaking wear set W from Galaxy J. We take some of J's input shares, process them, and generate a new wear set W prime, which should be identical to W. Since the shares are uniform, the adversary learns nothing about the secret if the simulation succeeds with only part of the input shares. Then let's talk about the security under the random proving model. In this model, the adversary samples each where independently with probability p. For example, when sampling the addition gate, each where gets lit up with probability p, and this creates a leaking where set W of observable wires. For such an adversary, the key security definition P epsilon RPS captures two crucial properties. And most cases with probability 1 minus epsilon, the leakage can be simulated by only part of input shares. Only in rare cases with probability epsilon, we need all shares to simulate the leakage. Since the shares are uniform, in most cases, the adversary can't learn the secret. And the epsilon failure probability gives us quantitative security. Then I want to introduce some previous works about random proof security. Some foundational contributions came from Balit et al. At Crypto 2020, which included a systematic verification framework and a composable security notion. The verification framework starts by assuming epsilon is 0. Then we exhaustively examine all possible leakage scenarios. Once a leakage pattern fails in the simulation, we add its probability to the growing epsilon estimate. As for the composable security notion called RPC, it is similar to RPS, but RPC introduced a threshold for output share leakage with number t, and the failure occurs when there are more than t input shares required for the simulation. It creates a security isolation between components, since one gadget's leakage won't affect others, except in those epsilon probability failure cases. Let me introduce the modular approach proposed by Anas et al. At Crypto 2018. Their key insight was by repeatedly compiling a circuit, we can drive its failure probability arbitrarily low while keeping the leakage probability constant. For example, when we compile the addition gates with addition gadgets, the leakage probability of the original wires becomes the failure probability of shares. And therefore, if the failure probability is lower than the leakage probability, each round of compilation reduces the overall failure complexity of the expanded circuit. This concept was later formalized by Balit et al. At Crypto 2020, introducing RPE. To be usable in such expansion framework, a gadget must satisfy two key requirements. The first one is composability, because the expanded circuit is built by composing base gadgets, and the security must survive this composition. The other requirement is independent failures. If the RPE gadgets has multiple input sharings, their failures must be independent, because the random proving adversary samples each wire independently, and the failure of the base gadgets should also align with the adversary's capability. Finally, let me introduce the amplification order, which is also proposed by Balit et al. In short, amplification order is defined as the smallest. It's defined as the size of the smallest leaking wire set that breaks simulation. It reflects the security level of a gadget, since the more wires the adversary must probe to extract wires, the stronger the protection is. On the other hand, to achieve target failure probability, high-order gadgets require fewer compilation. This means lower computational overhead while maintaining security. Now let me share the motivation behind our work. We identified two challenges behind the current RPE security security that demand a new approach. First, we find some operations like logic AND inherently create the dependencies. As shown in the truth table of the logic AND, the AND gate's output is correlated with the inputs, and the AND adversary can learn multiple words from simple observation. Besides, we find the RPE's independence assumption preserves security but creates inefficiency. If the joint failure probability of both share rings from one RPE gadget exceeds the product of their individual probabilities, this framework artificially increases single sharing failure probabilities. This led us to develop a new correlation-aware security framework. Then let me introduce the key innovation of our work, a tighter expansion framework that adapts to gate behavior. First, we categorize gates based on their statistical properties. Specifically, we define complementary gates, or C gates, as those whose output is independent with the inputs, while other gates fall into the NC category. Besides, we provide a new security notion called RRPE. It keeps all RPE requirements except the independent failure assumption. Our central result shows that secure expansion is still achievable if C and NC gates are expanded by RPE and RRPE gadgets respectively. Further in this talk, I will present some concrete results demonstrating that this method offers lower complexity than pure RPE without compromising on security. Since the RRPE gadgets are less complex, there is a natural question: can they be used to expand C gates? On their own, this expansion is not secure because the related failures are not allowed for initially independent wires. However, the situation changes when we add a virtual wire, creating a structured correlation between the inputs of C gate. We refer to these transformed C gates as VNC gates. In short, once the additional wire is sampled, the adversary learns both inputs of the C gates. Importantly, the extra wire doesn't alter the gate's original functionality. It merely introduces an admissible form of joint leakage from the adversary's perspective. Our paper demonstrates that VNC gates can be securely expanded by RRPE gadgets, meaning that RRPE-based expansion is feasible for all gates. To distinguish VNC gates with their original counterparts, we use a tilde notation. While the previous works provide a complete framework, there is still room for improvement, specifically in further reducing the complexity of the expanded circuit. Let me outline the motivation behind our improved expansion method. First, existing composable security notions are designed to handle worst-case composition scenarios, which demand more operations and randomness to ensure security. However, these extreme cases don't always occur in circuit implementations. As a result, these extra operations introduce significant redundancy. Especially, they are also expanded into multiple gadgets, leading to an exponential blow-up in the size of the expanded circuit. As shown in the slide, we address this by designing gadgets directly support the expansion of multiple gates together, rather than treating each gate in isolation. This targeted design reduces redundant components, shown as the red arcs in the addition gadgets. and leading to a more efficient expansion with lower overall complexity. To achieve this optimization, we first formally defined the composition of multiple gates and refer to them as half-complementary gates. They are composed of a fix of gate types, including C gates and VNC gates. To precisely capture the leakage correlation between the inputs, we introduce dependent sets denoted as A sub Q. If two input indices belong to the same set A, their leakage is correlated. If no such set exists for a pair of inputs, their leakage is considered independent. For example, the dependent sets of the HC gate REF are 1, 2, and 3, 4. So, so its inputs beta sub 1 and beta sub 2 are from the same VNC addition gate, and beta sub 3 and beta sub 4 are from another. In contrast, there is no dependent set like 1, 3. So the leakages of beta sub 1 and beta sub 3 are independent. Then let me explain how the HC gate can be expanded by MIRP gadgets. MIRP is a hybrid security notion that combines the properties of both RP and RRPE. It is specifically designed for gadgets involving multiple input sharings. Just like HC, MIRP also defines dependent sets to capture the correlation between input sharings. If two input sharings belong to the same dependent set, their failures are correlated. As a result, MIRP gadgets are well suited to expand HC gates, as long as they share the same dependent structure. For example, the REF gate can be expanded by an MIRP gadget with the same dependent set sets 1, 2, and 3, 4. To illustrate the benefits of our improved method, let's take a closer look at a concrete example of the expansion of REF gate. Under the previous framework, the RP addition gadget requires two refresh gadgets, each with at least linear complexity. The RRP addition gadget requires one refresh gadget, and the copy gadget also needs two refresh gadgets. As a result, a naive expansion of REF gate requires a total of 8 refresh gadgets, namely 4 from the 2 copy gates, 2 from the 2 VNC addition gates, and 2 from 1 addition gate. In contrast, our improved method constructs an MIRP gadget that expands the REF gate with only 4 refresh gadgets while maintaining the same security level. This approach effectively cuts the number of randomness and operations by about 50% for each expansion, demonstrating a significant gain in efficiency without compromising on security. Finally, let me introduce some concrete results that highlight the effectiveness of our new security notions and expansion method. For the RRPE notion, we proved that the well-known ISW multiplication algorithm proposed by Ishai, Sahai, and Wagner satisfies the RRPE security with optimal amplification order. This matches the performance proposed and Eurocrypt 2021 with complexity big O to n squared log n. Besides, our improved expansion method enabled the construction of 3-share and 5-share security compilers that achieved state-of-the-art tolerant leakage probability and complexity. Thank you.
Just in time. Any questions? We are anyway out of time, so maybe people can ask offline questions. Thank you.
Okay, thank you.
And the last talk in this session is Indiana. We are back to random probing security, so first and last. This one is on verifying it through indistinguishability analysis, and the talk will be given by Pascal Sastrich.
No, these are not my co-authors. Okay, yeah, so welcome to the last talk of today and the last talk of this session. In this talk, I'm going to explain you how to practically do verification for the probing and the random probing model, and in particular using our concept which we call indistinguishability analysis, or in short, Indiana. And this is a joint work with Christoph Bayerle, Jakob Feldkeller, Anna Guinet, Tim Gunesu, Gregor Leander, and Jan Richter-Brockmann. So before explaining our contributions and how to really do practical verification, let me just introduce a little bit of context and also give a short summary of our main motivation for this work. So in this work, we assume that we have a cryptographic device. So we have some hardware implementation of a cryptographic function. And as you all may know, hardware implementations or cryptographic implementations are, of course, or may be susceptible to so-called side channel attacks. So this means if an attacker can observe some passive characteristics of the device during the operation of the cryptographic algorithm, such as the runtime behavior of the device or the power consumption or the heat dissipation, then the attacker might be able to learn or infer some sensitive data just by processing these observed values. But of course, unfortunately, we have masking schemes to protect hardware devices and cryptographic operations in hardware against such attacks. But the problem is that the design and the construction, as we learned, is not trivial. And also, putting those constructions into practice is actually still a manual task. So it is still difficult and also an error-prone task to really implement masking schemes and hardware masking schemes in practice. So for this, the community has started to look at this problem in a more systematic way and tried to formalize the adversary models on the one hand, but also to really specify the environment of the device and also the architectural conditions of the device in order to compile them into security properties that we want to ensure. And the good thing is that these security properties, these formal specifications, we can use them to build automated security reasoning tools that we can then use in the context of hardware implementations to do some pre-manufacturing vulnerability analysis or detection in order to reason about the security of masking schemes even before going for production, and then do some post-manufacturing side channel evaluation. And as we already learned, so this slide hopefully is very familiar to you. We have mainly three models in the context of passive side channel attacks. So we have three different leakage models. The first one, which is the T-threshold probing model. And here, as you already learned in the first talk today, we assume that we have an attacker who can observe T intermediate variables and only T variables of the operation leak information to the attacker. The P-random probing model, of course, advances the T-threshold probing model. And here we assume that not only a single or T values are leaked, but all values are leaked, but just with a certain probability P. And then, closer to reality, we have the noisy leakage model, where we assume that we have some noisy information which is granted to an attacker, so the information is leaked, but it's just noisy information. And this model is, of course, closer to reality, but it's also the most complex model out of those three in terms of security reasoning. And as we already learned, there's this chain of security reductions, of course, with some loss in tightness, but the good thing is, if we do the verification or the security reasoning in the T-threshold probing model, this still gives us some way to argue about security in the noisy leakage model. And this is also the reason, because this T-threshold probing model is the simplest model out of those three, why most of the security reasoning tools focus on this model. And only a few started to look into the P-random probing model, but all of those models, they have some drawbacks, either being that they are restricted in terms of circuit structures or hardware structures they support, or they might be, their security arguments might be incomplete in the sense that they might exhibit false positives or false negatives. And this kind of led to our research mission or research ambition here. So our idea was that we wanted to develop a new tool that is sound, accurate, efficient, and exact. And it also should support arbitrary and more complex hardware circuits than previous tools, and it also should focus on more realistic models, such as the random probing model. And now this directly brings me to our contributions. So how do we actually do this, and how do we achieve this research mission? So for this, we went back to the T-probing model, the T-threshold probing model, and we assume that we have an attacker who has some access to a hardware circuit, which we model usually through some probes that an attacker can place in this model, or according to this model, on some wires in the circuit. And the first thing that we did, we tried to re-express the notion of probing security by just observing that if an attacker can place those probes on those wires and can observe the distribution of values, then the circuit is actually secure in the probing model if the attacker cannot distinguish different inputs or different values for the secret input X. So this means if the probe values, the distribution of the probe values is actually indistinguishable for different processed secrets X, then this circuit is secure in this probing model, and we can just say, just by being indistinguishable, the attacker cannot learn anything about the secret values. And so this was the first step. We formalized this view, and we also showed that this notion or this view is actually in line with previous definitions of the probing model. So we show that it is also in line with statistical independence, or notions based on statistical independence, but also based on simulatability. And in the second step, we also formalized this new definition in terms of a leakage function. So we define a leakage function that is based on some encoding scheme, which represents the masking scheme we are using, some adversarial axis on the circuit, which represents the probing scheme, and possibly some extension function which can be used to extend the probing scheme, for example, for the robust probing scheme, where we also consider additional physical defaults such as glitches or transitions. So the question now is, since this is just a formal concept, how do we actually put this into practice? So how can we derive the leakage function, which is at the core of our verification concept, in practice? And as I said, the idea is based on the fact that if an attacker cannot distinguish different input values X based on the distribution of the observed values, then we can argue about the probing security. So the idea is that starting with the distribution of the probe values, we in the end want to have a function that tells us about the leakage of the observations or the leakage of the circuit. So I'm now going to explain how, starting from these distributions, we can compute the leakage function. And the first thing is that we want to compare all the different observations of the attacker to each other. And in practice, we just do it by comparing all the different observations for all the different inputs and all the different secret values to the distribution of a fixed secret value. And without loss of generality, we simply use the secret 0 as our comparison. So we compute the difference of all observed values with the probability distribution for the secret X, and we take this secret or this difference function, and we just transform this function based on the fast Fourier-Hadamard transform. And in our paper, we show how this process actually links to the notion of T-resiliency and how we can use this to really compute the leakage function that we are looking for. Of course, this is not all. We have to do some post-processing on this step. I'm not going to explain the details here because those are just minor post-processing steps, so the details are in the paper. But basically, at the core of our concept is that we have the fast Fourier-Hadamard transformation that allows us to take the probability distribution of the probed wires and compute the corresponding leakage function. And we can use this leakage function then to actually reason about the security of our circuit in the probing and also in the random probing model. So the question now is, this is still rather theoretic, how do we really do this in practice? And for this, we mainly rely on two well-known data structures, which we know from computer science and also from the domain of functional verification. The first one is our so-called binary decision diagrams, or reduced ordered binary decision diagrams. And they are an efficient way to represent Boolean functions in a computer. So this is a graph-based structure, and based on a variable ordering, we can really find a concise and unique representation of a Boolean function, and we can also store and process Boolean functions this way. And we can also extend binary decision diagrams to so-called multi-terminal binary decision diagrams, where we have an extension and we can represent any function from a multidimensional Boolean domain to an arbitrary value set. So as you can see, it looks very similar, except that the terminal nodes are no longer restricted to 0 and 1, but we now have a finite set of multi-terminals for this data structure. And those two data structures are actually at the core of our verification tools, so we use them to implement this indistinguishability analysis. And mainly, we use the multi-terminal binary decision diagrams to represent the discrete probability distributions of the probed values of the attacker. And then we also show that we actually can use those data structures very efficiently. So there are some basic operations that are already defined for BDDs and MTBDDs, and we can show that the Fourier-Hadamard transform can actually be implemented very efficiently based on those fundamental MTBDD operations. So this is really where our concept benefits from this choice of data structures. I'm not going to explain more details on this, but I want to spend the last minutes on showing you some case studies that actually highlight the benefits, but also some of the limitations of our process. So as one of our case studies, we implemented and also we verified or analyzed an AES. And in particular, it's an AES round, which is implemented in hardware. So it implements 16 S boxes in parallel with the subsequent mixed columns operation. This implementation is actually pipelined. It takes 9 clock cycles to compute the output of the round function, and it's a first-order masked implementation. So we have 2 shares as an input and also 2 shares as an output. And here in the table, you can see that it actually, we analyzed it clock cycle-wise, and you can read the table as follows. In the first clock cycle, we have 16 independent modules, which actually correspond to the first clock cycle of the 16 independent S boxes. And we implemented and optimized our tool in such a way that it detects independent modules that actually process independent parts of the secret, and it also analyzes those parts independently. So what you can see here is that in the first cycle, we have 16 independent modules, and each module has actually 72 wires that an attacker can probe. And in order to limit the complexity of our verification, we granted 2 probes per module to the attacker, and this resulted in a total number of 2,556 combinations of 2 probes that the attacker could place into the individual modules. And we computed the Fourier-Hadamard transform and also the leakage function for all those combinations, and we accumulated the leakage functions to get a full leakage function for this first clock cycle. But of course, this leakage function is actually not complete, so there are a lot of combinations that we did not consider, and this is why we opted to compute for the leakage probability to compute a lower and an upper bound. And in fact, for the lower bound, we just assume that all the combinations that we did not consider, so that we did miss, are actually not leaking combinations. For the upper bound, we just did the opposite, and we assume that all combinations that we did not verify, that we did not check, are actually combinations that do leak. And this gives us a way to compute an upper and a lower bound for the leakage probability. And as you can see, for the first cycle, this process took about 1 minute. In total, for the 9 clock cycles, this took about 4 hours, less than 4 hours. And you can also see in the last clock cycle, which actually implements the mixed columns operation, we just have 4 independent modules because each mixed column operation combines the output of 4 X boxes. Right. And maybe something that is interesting here to see is that clock cycle 7 seems to be the clock cycle where we have a very high leakage probability. And this clock cycle still corresponds to the S-box computation. So our second case study was that we wanted to zoom a little bit more into this S-box. So we also analyzed just a single S-box. And here you can again see the red curve actually corresponds to the upper bound. The blue curve is the lower bound of the probability distribution. And you can see that for this single S-box, the leakage probability is actually highest in the 7th clock cycle, and there's also some higher leakage probability in the 2nd clock cycle, which actually also corresponds to the nonlinear parts of the circuit that we implemented. So we have a Galler field inversion here, and the nonlinear parts are actually performed in the clock cycle number 7 and clock cycle number 2. And out of curiosity, we also performed some practical side-channel evaluation, and surprisingly, it also seems to confirm that we have some high second-order leakage in clock cycle number 7. So there seems to be some correlation or some correspondence between our theoretical verification results and the practical evaluation. But of course, this is not really a complete analysis, so this is future work, how this really links or relates to each other. Right, and since time is almost up, let me just quickly wrap up what our contributions are. So our first step was that we formalized our the concept of probing and random probing security in terms of indistinguishability analysis. We then show an efficient and fast way how to derive the leakage function using the fast Fourier-Hadamard transform. And we also implemented all this theoretical concept in terms of a practical verification framework that is open source, and you can find it on GitHub, or you can just use the QR codes here to look up the tools. And with this, I would like to thank you for your attention, and I'm happy to answer any questions.
Is there a question for Pascal? Yes, I think everybody's tired. Just a quick one. So we saw post-quantum in the first talk and random probing security. So do you see Indiana extended to post-quantum implementations?
Yeah, I think out of the box we can't do post-quantum because I kind of didn't explain this, but here we simply focus on Boolean masking, and usually post-quantum schemes, they don't work on Boolean masking. But ideally, since our mission was to analyze arbitrary circuits, at some point we want to go for post-quantum schemes as well.
So some interesting future work, say.
Exactly.
Okay, let's thank the speaker and all the speakers of this session, and we conclude for today.